works. Thank you.
Yeah.
Go ahead.
Okay. The title is Non-Symmetric Metric Tensor as an Approach for Quantum Gravity. The main problem is that we know that the Einstein field equation relates classical geometry with the quantized energy momentum tensor. My proposal here is to try to understand whether the minimal length, as proposed by the GOP, the generalized uncertainty principle, could enable us with a kind of quantization, if not a kind of discretization of the space. In doing this, I'm going to confront these results with the Einstein field equation. I'm starting here with the metric tensor itself, with a line element, and with the geodesic equations. Problem. Sorry. Now. Okay. Also
everything
now
seems to work fine.
Very good. The GOP minimal length was proposed a long time by Kempf, Monjano, and Martinez, and you can see accordingly that the minimum length is in the order of the square root of h part g, the gravitational constant, divided by c cubed. There are various proposals for the GOP minimum. For example, Giori also proposed another one based on quantum deformation of the Poincare algebra, and accordingly the minimum length takes this form, which is the square root of gamma 0. Gamma is the GOP parameter, and also this beta appeared in previous expression are also both are also GOP parameters, which could be determined from other experiment, thought experiment, or even from inspired by the GOP, the canonical commutation relation for quantum operator can be expressed in this way, and also similarly we can express also the the corresponding commutation relation for the operators themselves. The main idea is that the non-commutation relation can be included in the space-time geometry through enlarging Minkowski manifold to an 8-dimensional space-time. For instance, this is the x to 8, x to a, and a goes from 0 to 7, the 8-dimensional quantity, and when we do a line metric in the 4-dimensional space, this is the left-hand side, and the modified Minkowski line space. Almost the same where we have here mu, and here we have AB, and AB, as I said, AB and capital or small goes from 0 to 7, and the Greek letters mu, lambda goes from 0 to 3. Coming back from 8-dimensional, the 4-dimensional space, we use this expression, and accordingly we can have a kind of expression for the metric tensor g mu tilde, which is given by this expression, which could be summarized in the far right-hand side, square 1 plus beta x double dot lambda all multiplied by g mu nu, the uncorrected one. This means that we get some correction to the g mu nu. And in flat space, we can express also g mu nu in this expression, where h mu nu equals beta lambda double dot lambda x double dot lambda and x double dot lambda eta mu nu. The same can also be done for metric, and you can see here the ds tilde squared equals ds tilde squared multiplied by this bracket 1 plus beta squared lambda double dot lambda x double dot lambda and x double dot lambda and so on. This is a correction term according to the GOP approach. Also, we can equation in a flat space. We get this expression which contains the additional parameters, and in curvature space we have a very complicated expression for the geodesic equation, where the various parameters below. What we have right now, we can conclude, at least from the geodesic equations, that our result means that not only acceleration x double dot of the test particle in the gravitational field is increased. If you can review again this expression for the geodesic equation, you have higher derivatives of the x, not only the second one. Namely, we have snap, we have choice, and we have even jerk. The acceleration, which already have observed in astrophysical observation and awarded the Nobel Prize a couple of years ago, now we have some approach to explain the origin of the expanding acceleration. Means that we are, the space is not accelerated, but also has higher order derivative of the acceleration and so on. Jerk and the snap jerk, for example, gives the change of the force acting on that test particle, and the snap is resulted from the change of the jerk itself. Both quantities are finite when the vibration occurs, especially for multi-resonant modes, and for sudden transition between different radii of the curvature. To summarize here, these are the approach of the GOP, where the operator X and P are given by this expression, where beta appears here as a correction due to the GOP. When we apply this to geometric tensor, we have some correction in form of beta square x double dot x double dot. And also the line metric also gets another expression or another correction, and the geodesic equation, if I limit for the flat space, we have in this form, are for the curved space, we have in this form. As for the title of the talk, which goes to the symmetric properties of the metric tensor, I can just tell you that this calculation are still under.
I'm sorry, we lost you.
Yes.
Yeah, please continue, because we lost you for a second.
Yeah, I'm finished at least. I have to summarize my talk. That the metric tensor obtained even for the GOP remains symmetric as the original one. This is the main conclusion of my talk.
Okay, thank you very much for your talk. I'm sorry that it was necessarily so short. I think that we're still on, so if there are any questions, please ask.
Yes, sure.
Okay, I don't see any questions, so thank you everyone for taking part in this second session of quantum gravity phenomenology session, and we meet again tomorrow at 9:30. Goodbye.
Bye-bye.
Thank you. Goodbye.